Welcome to The Explainer. Today, we're taking a truly fascinating journey under the hood of modern artificial intelligence. If you've ever interacted with a large language model and just marveled at its ability to understand context, write code, or draft entire essays, you're actually witnessing the magic of something called the attention mechanism. Our focus today is demystifying this exact mechanism that's basically powering the entire AI revolution. And don't worry, we're going to do this intuitively, without getting bogged down in impenetrable math.
So let's dive right in by asking a pretty foundational question. How does an AI actually resolve context? For instance, take a look at the sentence on screen. The animal didn't cross the street because it was too tired. When an AI processes this, how on earth does it know that the word "it" refers to the animal and not the street? Well, the secret sauce is attention, a system that lets the model look at all the input words and dynamically decide that animal is the absolute most relevant word for resolving that pronoun.
To really wrap our heads around this, here's our roadmap. We'll start with the bottleneck problem of early AI, break down the core mechanics of queries, keys, and values, look at scaling up, tackle the massive memory crisis that attention accidentally created, and finally, scope out the post-transformer frontier. Starting with Section 1, the bottleneck before attention. Let's rewind the clock just a bit to the early 2010s, when AI relied on recurrent neural networks, or RNNs, to process sequence tasks like translation. The fatal flaw with those old RNNs was literally called the bottleneck problem. It basically required forcing an entire sequence of data into a single, fixed-sized vector. Imagine trying to cram an entire thick novel into just one single paragraph before you hand it off to a translator. It's impossible, right? Critical early information would just get totally lost or diluted by the time the AI actually tried to generate an output. And that brings us to a really stark contrast. See, RNNs had to process data sequentially, literally word by painstakingly slow word. It was highly forgetful. But then, the 2017 Google breakthrough happened, the famous "attention is all you need" paper. It introduced the transformer, and the game changer here? Transformers process all tokens simultaneously. They dynamically weigh the context of every single word against every other word, all at the exact same time. Moving on to Section 2, queries, keys, and values. So how does a transformer actually pull off this parallel processing magic? It all comes down to self-attention, the engine deciding what to focus on at any given millisecond. To picture this mechanics without drowning in linear algebra, just think of a massive library database. You've got three main components: queries, keys, and values. Your query, that's what you type into the search bar, what the AI is currently looking for. The keys are like the index tags on the books, and the values are the actual contents of the books you want to retrieve. The AI simply compares your query against all those keys, scores them for relevance, and hands you back a perfectly weighted combination of the values. Now, what's absolutely brilliant is how that exact library analogy translates into this beautifully compact equation you see here, scale dot product attention. The model computes the similarity between queries and keys using a dot product. Then it scales that number down by a square root. Why? To keep the whole system mathematically stable and prevent vanishing gradients. Finally, it runs it through a softmax function, which elegantly turns those raw scores into probability weights that always perfectly sum to 1. Which leads us to Section 3, scaling up multi-head attention. Because, let's face it, human language is messy and multi-dimensional. One single attention mechanism looking for one type of relationship just isn't gonna cut it for capturing all that nuance. And that's exactly why modern models use multi-head attention. Instead of just doing one pass, the AI runs multiple attention computations completely in parallel. It lets different heads specialize. Think of it like a team of experts. Head A might be the grammar nerd, making sure subjects and verbs agree. Head B is the detective, hunting down pronouns to see who he or it refers to. And Head C might just be looking at words that are right next to each other. It's processing all these layers of meaning at once.
But there's a slight catch here. Because attention processes everything simultaneously, it's mathematically permutation invariant, meaning if you scramble the words, it doesn't know the difference. It has no innate sense of time or order. So to fix this, engineers inject positional encodings. A super popular method right now is ROPE, or rotary position embeddings. It essentially mathematically rotates the vectors, so the AI gets a built-in sense of which word came first, second, third, and so on.
Okay, Section 4, solving the memory crisis. So here's the kicker.
While this amazing attention mechanism totally solved the old RNN bottleneck, it accidentally unleashed a massive new villain, the memory crisis.
You see, standard self-attention has what computer scientists call an ON squared, or quadratic complexity. In plain English, if you double the length of the text you feed the AI, the computational and memory cost doesn't just double, it quadruples. If you're processing a couple of sentences, sure, no big deal. But if you want to feed the AI an entire book or millions of lines of code, the memory requirements absolutely explode to an unmanageable size.
So engineers had to get seriously creative to shrink this massive memory footprint, specifically in the key value cache. We started with standard multi-head attention, which was a total memory hog. Then we evolved to grouped query attention. This cleverly groups heads together to share key and value data, slashing memory needs way down. This is actually the engine inside models like Llama 3 and Mistral. And most recently, multi-head latent attention. This highly compressed method shrinks keys and values into a tiny latent vector, keeping memory minimal, and it's exactly what powers DeepSeek V2.
And this ties perfectly into another massive, absolute game changer, flash attention. Now, this isn't tweaking the AI's brain. It's a brilliant software hack for the hardware itself. Standard attention was constantly bottlenecked by moving huge chunks of math back and forth from the GPU's slow memory. Flash attention reorganizes that math into tiles, keeping the whole process right on the GPU's ultra-fast SRAM chip. The result? It speeds up processing by 2 to 4 times without losing a single drop of mathematical exactness. It's pure genius. Finally, we arrive at Section 5, the post-transformer frontier. Because despite all those brilliant optimizations we just talked about, as we try feeding AI sequences of millions of tokens at once, pure attention mechanisms are fundamentally hitting a physical wall. So, what's next? The frontier of AI is actively hunting for subquadratic alternatives. You've got sparse attention, which tries to save on math by only looking at carefully chosen subsets of words. There's linear attention, attempting to completely rewrite the core math to scale linearly instead of quadratically. But honestly, the most exciting shift right now is towards state space models, or SSMs, like Mamba, which inherently process in linear time. We're even seeing hybrid architectures like Jamba, mashing up transformers and SSMs to get the absolute best of both worlds. Looking back at our journey, the evolution has been ridiculously fast. We started the early 2010s trapped by sequential RNN bottlenecks. Then 2014 brought early NLP attention, which exploded into the 2017 transformer revolution. 2022 broke the hardware barriers with flash attention, fast-tracking us right into today's era, defined by linear time models and crazy hybrid architectures. Which leaves us with a pretty provocative thought to chew on. If the attention mechanism was literally invented to replace RNNs and solve the bottleneck crisis, what's ultimately going to replace attention to solve the memory crisis? As AI models continue to scale up to process entire lifetimes of data in one go, the next massive revolution in sequence modeling is probably being engineered right now, as we speak. Thanks for hanging out with me for this explainer, and definitely keep your eyes on the frontier.